Well, it's a great pleasure to be here at this meeting. And as a cosmologist, I thought it would be good to talk about this issue on this 100th anniversary, the role that general relativity has played in the rise of cosmology. And there will be 9 sections here. I'll talk about consistent cosmological models, curvature and the topology of space, the expanding and evolving universe, a start to the universe, null cone observational tests, observational and causal limits, that is horizons, structure formation and inhomogeneity, gravitational lensing, and a consistent picture. So this is what I want to talk about in this discussion. So the first thing that general relativity did was it allowed the first cosmological models to be developed. And it was known that there were problems with Newtonian models. Now, I haven't been able to properly trace up what Newton and Laplace said about it, but there's a famous paper by Seeliger in 1895 pointing out that if you try a Newtonian cosmology, you get inconsistent pictures because of the divergences. If you use a force law, because you're thinking of the force on a particle in an infinite universe, depending how you break up that infinite universe into cells with forces acting on the particle, you can get any answer you want. And this is just part of the problems you always get with infinities. So Newtonian efforts to derive a cosmology simply did not, either they weren't tried or they didn't happen. And the first proper cosmological model was Einstein's static universe model in 1917. And this established the basic proposition that the local effect of the gravitational field everywhere can give you a consistent universe model. So Einstein's field equations applied everywhere, the matter curves space-time, and you get a consistent universe model. Now, these models were static, and in order to make them static, Einstein had to introduce the cosmological constant. And this is a well-known story that if you don't have the cosmological constant, you cannot get a static model. So why did Einstein believe the universe was static? Well, the answer is everybody believed the universe was static at that time. It was taken for granted by all the major figures in cosmology: Eddington, De Sitter, Einstein. It was just taken for granted this is the way it must be. And this is a warning to theoretical physicists and other physicists that you need to be able to question the wisdom which is taken for granted by all the big figures in the field around you, because all the big figures did. Now, the Einstein static universe is unstable, and Eddington proved that. It's very easy to prove that using the Raychaudhuri equation. And if you understand that the Einstein universe is unstable, this should lead you to believe that actually the universe should be either expanding or contracting, but it shouldn't be static. And this was basically the direction that Eddington was going, and Eddington would have discovered that the universe was expanding or contracting if it hadn't previously been discovered by Lemaitre and Friedman. But the point about the present slide is that the Newtonian models of cosmology came much later. They came with McRae and Milne in 1934. But I must add a caveat in here. These are called Newtonian cosmological models. Now, they're not really Newtonian. They are generalized Newtonian theory. And Heckman and Schücking wrote about this very, very well, because if you take the Milne and McRae models, there's a central world line which is geodesic. Now, the other world lines are accelerating away with, in the simple cases, the scale factor A is proportional to t to the 2/3. What that means is, relative to the central world line, these other world lines are in fact accelerating. And so the only geodesic world line, the only freely falling world line in the Newtonian cosmologies of Milne and McRae, and even Peebles and all the others, is the central world line, and none of the others are in fact freely geodesic. And in order to talk about a spatially homogeneous Newtonian model, you must introduce a new idea, acceleration with a capital A, which is the force of acceleration plus inertia. And this is what Heckman and Schücking did. And if you introduce that idea, then all the models have exactly the same value of acceleration plus inertia, naming 0 in the pressure-free case. And this is, of course, because in general relativity, you cannot distinguish acceleration from inertia. So they're generalized in that sense, that they are not standard Newtonian theory. And the second way in which they're generalized is that the standard conditions for the potential at infinity in Newtonian theory do not hold in Newtonian cosmologies. If you use a field theory of the derivation of Newtonian cosmologies, the field diverges at infinity quadratically. And so there's a very interesting sort of story here that the first cosmological model was Einstein's static cosmological model, followed very shortly by de Sitter's ones, but de Sitter is an exception because it's really empty space, and I haven't talked about that there. And the Newtonian models came much later, but when we say Newtonian models, they are not Newtonian models in a strict sense, they are generalized Newtonian models. Okay, now, the second thing that Einstein model brought in was the curvature and topology of space. And his models were all the models, they have the standard Robertson-Walker metric shown there. You have you have the time, and then you have a scale factor, and then the spatial sections, and you've got a factor f of r there, which is sine r, or, that should say sinh. Sorry, that's a typo. It should be hyperbolic sine or r or hyperbolic sine if the spatial curvature is +1, 0, or -1. And so these are three spaces of constant curvature. Now, the geometry of three spaces of constant curvature was very well known since the time of Riemann. And what this means is the spatial sections need not be flat. Now, this was a huge step because what this means is the assumption that Euclidean geometry would hold in the universe was found to be untrue. And Jürgen Ellis has emphasized that initially when Einstein thought about gravity causing curvature, he wasn't thinking of gravity causing space-time curvature. Initially he was thinking of gravity causing spatial curvature. And that is exactly what is happening here, is you're getting spatial curvature in the cases of the positively and negatively curved models. The spatial sections need not be flat, Euclid's undermine. Now, the further point that comes in, which is a major point, is that in the case k is +1, the universe is necessarily spatially closed, and that's a simple geometrical argument, and in fact it was known, as I said, to people like Riemann and so on, that if you go off in that direction in a spatially curved universe, you will come back from that side. If you go that way, you'll come back that way. And if you go that way, you'll come back that way. They are spatially curved three-dimensional analogues of the two-dimensional surface of a sphere. And so not only is the space curved, but it can have a topology which is quite different from the Euclidean topology. Now, it's been known for a very long time that k is +1 necessarily implies closed spatial sections. K is 0 and -1 allow closed space sections, and it is not true that if you have a k is 0 or -1 model that it necessarily is open with the infinite space sections you first thought of. And this has been also known for a very long time. And in fact, in the case k is -1, there are an infinite number of possibilities, and these have been explored by many people such as Thurston and others. There's a catalogue of negatively curved spatial sections. So we end up here in general relativity not just with space-time being curved, we end up with space being curved, and we end up with the spatial sections having topologies which one might never have thought of in the first case. So this is a radical departure from Newtonian theory, where spatial sections are Euclidean spatial sections with the flat, simply connected Euclidean topology. Now, there's a further point which comes through all of this, which is very important, is that in the real universe, there's always a preferred four-velocity field. The Lorentzian variant of general relativity is broken for cosmological solutions. So there's a preferred four velocity, and this is Weil's principle of having preferred time-like lines, and Jürgen Ellis developed this. And so, for instance, astronomers measure the average motion of matter in a volume around us. Nowadays, the way to determine the preferred four velocities by measuring the cosmic background radiation rest frame. There's one and only one rest frame in which the cosmic background radiation is isotropic, and so as astronomers measure this preferred velocity to great precision by finding out in which rest frame you get rid of the dipole and the cosmic background radiation. Geometrically, the preferred frame is the Ricci eigenframe, because that comes purely from the purely from the geometry of the space-time, and of course, because of the field equations, that is also the matter stress tense eigenframe, so it's the Landau frame of general relativity. And in a Robertson-Walker model, these all coincide. In a perturbed Robertson-Walker model, they will not necessarily be the same, and you have to choose between them. And almost certainly the best frame is the last one, that is the Ricci eigenframe. But anyhow, it's an absolutely fundamental feature of cosmology that in the real universe, it is not true that Lorentz invariance holds. It's a broken symmetry. Of course, broken symmetries are a major part of physics. And so space and time are split into space and time by this four velocity. So there's a four velocity and there's a metric for the rest spaces. And so HAB is the metric for the rest spaces of the observers moving with four velocity UA. H is defined as G plus UU. Oops, sorry, that's another typo. That should be a U. It's a projection tensor. It projects U to 0 and, oh, sorry. HAA is 3. That should be a 3. So it's a projection tensor. It projects U to 0 and its trace is 3, which means it projects into a three-dimensional spatial surface at each point. And then with this, you can project any vector into a parallel part and a perpendicular part. You can take the dot derivative, which is the derivative along the world lines, and you take the d derivative, which is the projected derivative orthogonal to the world lines. And so in general cosmologies, when you're doing cosmologies which are not exactly Robertson-Walker, in particular perturbed models, you can use the splitting of space and time into space-time into space and time in order to analyze what a local observer would measure. And of course, a local observer has a rest frame and has a preferred velocity and has a preferred derivatives, and that's what this formalism gives you. And from this viewpoint, the problem with de Sitter and anti-de Sitter spaces is there is no preferred four velocity because they're space-times of constant curvature. And in the early history of cosmology, there was a great confusion about de Sitter space because it wasn't understood that there are many different possible frames in de Sitter space-time. From the viewpoint of present-day cosmology, that's because de Sitter and anti-de Sitter simply aren't good models of the real universe. Okay, now, given these field equations, we then get the idea of the expanding and evolving universe. Geometry is physics. Gravity governs the space-time of cosmology. And so what we then was discovered in 1922 by Friedman and then 1927 by Lemaitre is that you can have dynamic models with the geometry I just wrote down, a scale factor A of t, which represents how matter is moving apart or contracting as the universe evolves. And it has three equations. The Ray-Choudhury equation, which is the equation of gravitational attraction. It gives you the second derivative. It's a force law, if you like. And the crucial point here, the active gravitational mass is rho plus 3p over c squared. And this is completely different from Newtonian theory. It comes from the form of the Einstein field equations, and it's one of the reasons whereby the singularity theorems of general relativity are so much stronger than the corresponding singularity theorems of Newtonian theory. The point is, in Newtonian theory, you think of a pressure as preventing collapse. What this tells you, it's a fundamental feature of general relativity, is the higher the density, the more it makes the universe collapse, because this is the curvature of A of t as a function of time. And if it's negative, it's tending to make it curve down. It's saying that gravitational attraction is making the curve A of t curve downwards. And Density makes it curve down, but the pressure does it well. So if you pile on pressure to try to resist the gravitational collapse, it makes the situation worse. And so that's the Raychaudhuri equation. Then you have the Friedmann equation, which is the first integral of the Raychaudhuri equation, and it's an energy equation: kinetic energy, the gravitational potential energy, the cosmological constant energy, and the K, the constant. And if you and then you have the conservation equation, which is rho dot plus 3a dot of a rho plus p is naught. And any two of these equations implies the third one. In fact, this is the first integral of these other two, and k is the integration constant. And so what you find is that the integration constant for the Raychaudhuri equation and the Friedmann equation is nothing other than the spatial curvature. Now, what is also important in this is that there's an equation of state assumed. These equations only close if you have the equation of state. And so this is the thing that the matter drives the geometry. Different equations of state will give you different outcomes from these equations. So these, of course, are the standard equations for cosmology, which have been known since at least the early 1930s. And they have this standard kind of form. This is for the case of a vanishing cosmological constant. You've got a competition between kinetic energy and potential energy. The spatial curvature is linked to recollapse, and you define the dimensionless parameter omega is 8 pi g rho over 3h squared, where h is the Hubble parameter. It takes the value 1 for the critical case. It's greater than 1 for recollapse, and it's less than 1 for the ones which expand forever. Life is more complicated when lambda is not naught, but the k is plus 1 models recollapse. K is naught are the borderline ones, and the k is minus 1 are the ones which do not collapse. And that, of course, what they all share in common is they start at an origin where the density, the radius goes to 0. And so one of the major features, so what we had there was that the universe is dynamic. And as I've said, this was a huge surprise to everybody. And in fact, what is one of the, in a sense, shameful episodes of the history of cosmology is when Friedmann wrote to Einstein and spoke to Einstein and said, look, there are these models of dynamic universes. And Einstein said to him, first he said, your mathematics is wrong. And then it was pointed out to Einstein the mathematics was correct, and Einstein then said to Friedmann, your mathematics may be correct, but your physics is abominable. And this, as I say, it's one of the cases that Einstein really seriously got wrong. Okay, now, sorry, one other thing I must just say here about this. The difference from Newtonian theory is the p in there, but it's also the p in there. Sorry, that should really be a p over c squared. And this also makes the singularity in general relativity worse, because again, the higher the energy, the higher the pressure, the more rapidly the density builds up. So as you head towards the singularity, this says that adding more pressure makes you, the curve of A as a function of t bend down more and more. And this one says the density goes up more and more rapidly the higher that the density is. Okay, so now we need the energy conditions. The first standard energy condition is rho plus 3p over c squared is greater than or equal to naught. And the second is rho plus p over c squared is greater than or equal to naught. Now, all the ordinary matter you've ever come across satisfies those energy conditions. And so if they are true, then it's just as simple. Take the Friedmann equation. If the Hubble constant is positive at some time and lambda is less than or equal to naught, then a finite time ago, the age of the universe is less than 1 over h naught. A finite time ago, A goes to 0 and the density goes to infinity. That follows from the conservation equation, and that follows from the Raychaudhuri equation. Now, we've somehow got used to this, and we talk about the singularity at the start of the universe. We kind of just talk about it, but actually, if you think about it, it is a huge crisis for physics, as John Wheeler particularly emphasized. It's a start to space, to time, to space-time, and it's a start to the physics itself. And that means it's a real crisis for physics, because this is the first time that we have predicted that physics comes to an end if you go backwards in time, or that the universe from a scientific viewpoint had a creation time before which the physics simply didn't apply, because this energy density blew up as you went down there, and you can't extend through in any well-defined way to previous times through that singularity. It's a Ricci singularity, it's a scalar singularity, and space-time diverges there. Now, of course, those singularity theorems, that's the singularity in the case of the Robertson-Walker model. So people then, particularly in the 1960s and early 70s, said, well, okay, maybe that's a result of the very high symmetry of these models. So there was this huge work that went on. The basis of the singularity theorem in general is the Raychaudhuri equation, and this is the general version of the Raychaudhuri equation given by Jürgen Ellis in a beautiful derivation. The time derivative of the expansion plus a third the expansion squared plus twice the shear squared minus the vorticity squared minus the divergence of the acceleration plus a half kappa rho plus 3p over c squared minus lambda is naught. That's completely general. It's true in every space-time for a time-like vector field. And it says that shear tends to make the thing collapse towards a singularity. It says vorticity can potentially prevent a singularity. It says the acceleration, that is the time derivative, the degree to which the four-velocity field is non-geodesic, can go either way, because that divergence can have either sign. It says the active gravitational mass is rho plus 3p, and it says lambda can act either way depending on the size of lambda. A positive lambda will tend to prevent a singularity. Now, a huge amount of effort went into trying to use these equations and the full equations of general relativity to see if there were or were not singularities in general space-times. And we heard yesterday about Belinsky, Kalatnikov, and Lifshitz, and in Bianchi universes, myself, Larry Shepley, other people, Stephen Hawking, various people looked at that. And it turned out by using simple analytic methods, that is taking the Einstein field equations and working them out and using them as dynamical systems, people were unable to prove whether a singularity existed or not. And then Penrose came along with his startling paper in 1965, the wonderful paper where he introduced global methods and he applied them to black hole singularities. Stephen Hawking, a year later, applied them to the singularity at the start of the universe, which in a sense is a reversed black hole, because in the black hole you've got trapping surfaces in the forward direction of time. In cosmology you have them in the reverse direction of time. And using analyses depending on the domain of dependence, the boundary of the future, and the null-Raychaudhuri equation, singularities must exist provided energy conditions are satisfied, but these theorems didn't tell you what type of singularity would occur. So the singularity theorems said there will be a singularity, but didn't specify the type. Now, when Guth and others came along with inflation, this changed things a bit, because in inflation, the density of a scalar field is a half phi dot squared plus v of phi. The pressure is a half phi dot squared minus v of phi. So rho plus 3p is 2 phi dot squared minus 2 phi, and that can become negative if you have slow roll. So if that term is very small, all of a sudden you lose the energy equations. That term can change sign, and in principle you can get models which are not singular. Now, just out of fun, I'll point out a paper which I and some colleagues put on the archive a few days ago. We've come up with a rather nice model of a cyclic model in which there is no singularity in the past for various models. Now, what this is, it's a rather interesting diagram. It's a diagram of omega, the parameter I said to you, but what you have to realize is the following. If you have a model which expands to a maximum and then comes down at the maximum, omega, that parameter, diverges, because remember, it's kappa rho over h squared. At a maximum, h is 0, so this is infinity. So here, omega goes from 0 to 1 to infinity, and then from infinity to 1 to 0. And a cyclic model like this one, it cycles round, and omega is between infinity and 1. Omega is 0 there, is infinity there where it diverges, but that's just a coordinate singularity, and this one cycles round and round, and that's not usable as a model of the real universe. in all Robertson-Walker models, the omega, if omega is 1, the total omega, that is the total curvature of space-time, that is a strict invariant. It represents the spatial curvature, and spatial curvature cannot change. If the spatial curvature is +1 at the start of the universe, it must be +1 through the entire history of the universe. For 0, the same, and for -1, the same. And the interesting models are the one where the curvature is positive, and you can get a model which goes through an inflationary phase. It expands. So this is inflationary phase. This is radiation-dominated, matter-dominated. Then it becomes cosmological constant-dominated. But if you have a model where you have a decaying cosmological constant, now this may or may not happen. Current dark energy may or may not decay. If it does decay, eventually you reach a time over here where the matter dominates again, and so this model, it's going up like that, it's going down like that in the cosmological constant denominator. It goes up, goes through, recollapses, and it does a cyclic motion all the way around there. And so you can get, purely in general relativity, models which are cyclic. This goes against some claimed theorems by Guth and Vilenkin and others. Those theorems are maybe good mathematical theorems, but they are constructed to exclude cyclic models such as this one. There's a whole discussion you have to go into about what would happen on the cyclic model as you come down here. It relies on turning on inflation down here, and it relies on that violation of the energy condition in the collapse here to give you a regular bounce through general relativity, no extra equations, no higher dimensions, no alternative field equations. So you can get cyclic models in standard general relativity if you allow the cosmological constant, which is presently accelerating the universe, to die away in the future. That is a possibility which may or may not be the case. What is crucial to this model is it must have k is +1, the k is -1 models all do not behave in that way. Okay, now these are mathematical models. To relate them to observations, you must trace light rays and photons. So you must calculate the null geodesics in these models, and there's the null geodesics relate to a phase phi. You calculate redshifts, and it's been known for a long time, since Weil, Schrödinger, and others, that the general formula for the redshift is you take the scalar product of the null vector with u at the observer divided by the scalar product of the null vector with the observer at the emitter, and that gives you the redshift. You need to work out the luminosity distance, which is how much null rays are. If a bundle of light rays sets off from the source, it'll diverge, and because this is a curved space-time, it won't diverge the same way as it will do in flat space-time. So you've got to work out how it diverges. That's the luminosity distance. There's a reciprocal distance. So from the source, the null rays diverge coming out to the observer. That's the luminosity distance. From the observer looking back at the source, you look down and you see the apparent size of the source. That's the angular size distance. And so the angular size, apparent angular size alpha, is proportional to the size of the object times the angular size distance. The luminosity is proportional to the inverse square of the luminosity distance. And they are related by a fundamental theorem, the reciprocity theorem, which says that up to a redshift factor, this distance is the same as that one. Now, Etherington proved this way back in the 1930s. It's trivial to prove in the case of Robertson-Walker models, but it's true in general, and this was discovered by Penrose and Sachs, rediscovering the results of Etherington, which was in the 1930s. If anybody ever proves the reciprocity theorem is wrong, then there's a crisis for general relativity, because it depends simply on the fact that that light rays prove on null geodesics. So a very interesting question is, can you test the reciprocity theorem? And there's a couple of papers out now on how you can test the reciprocity theorem. And one of the ways you can test it is by looking at the cosmic background radiation spectrum, because one of the most uncelebrated results in all of this theory is the following fact. If you have black body radiation emitted at the surface of large scattering and it travels through space, it remains a black-body spectrum. And it remains a black-body spectrum because of the reciprocity theorem. And so if you find that the black-body spectrum does not remain a black-body spectrum exactly, precisely, then you have a violation of the reciprocity theorem. Okay, number counts. You have the number density of sources and the distance. You have a little volume of space-time, the distance you go along, and the solid angle gives you a volume, and you can work these out, and you can get there for observable relations, and the classic ones are the magnitude redshift relation and the number count redshift relation for galaxies. And the huge discovery of the late last century is that we live in an accelerating universe. And this was, of course, the Nobel Prize that was awarded to Schmidt and Rees. And this curve, if we weren't accelerating, we would be on a straight line. And incidentally, Hubble's data was a tiny little corner in the bottom. We've extended Hubble's data to a huge degree. The problem with all of this is you need a standard candle. If you don't have a standard candle, you can't do this test. It turns out that supernova type 1a are standard candles, and you use them, you find out the redshift is going this way, and the magnitude is going that way, and it's not on the straight line, it's rising above. The universe is presently accelerating, which means at the present time, rho plus 3p over c squared is negative. There is some kind of dark energy, or else there is a positive cosmological constant. And this was a big surprise, but let me just add something. It was in fact anticipated by studies of structure formation. If Staffio and co-workers said that you should have a cosmological constant before the supernova data on the basis of structure formation studies. So now, the key thing that happens that we must further take note is there are particle horizons.
Because some people may not know what you mean by a standard candle.
Oh, the standard candle. Sorry. When you're looking, okay, when you're looking there, in order to interpret this, you're looking at the brightness of galaxies as a function of redshift. Now, the theory will tell you what we should observe as a function of the brightness of the source when it gave off the radiation. And so you need to find a family of sources, all of which have got exactly the same brightness over there. Now, the trouble is that galaxies have a huge variation, so you can't use galaxies as standard candles because they vary too much. Radio sources vary even much more. Quasi-stellar objects even much more. And so the problem was to find a set of sources that you could be confident how bright they were over there, so that when you measure their brightness here, you can relate them in a unique way. Okay, now, there are these limits. There are limits on causality given by the particle horizons. There's limits on what we can see given by the visual horizons. And there's limits on the event horizons. Event horizons relate to the very far future of the universe, and they have nothing to say about observations in present-day cosmology. You might get confused about that from some of the literature which talk about event horizon in cosmology, but by the definition of event horizon, an event horizon is a limit on what you will ever be able to see at the very, very far end of your history in the universe. They relate only to t goes to plus infinity. They have nothing to say about what we can see now. So they have no effect on observations. But the ones that do matter are the other ones. Now, this is a very nice diagram by Ned Wright showing this is a space-time diagram with proper distance against time. And our past light cone, if you work it out, goes out to a maximum distance and then goes back in. And this is the refocusing of the past light cone due to the gravitational effect of the matter inside it. Now, in fact, Fred Hoyle discovered this way back in the early 60s because the angular size of objects has a minimum there. If you move a fixed object back further and further away from us, it will look smaller and smaller it will reach a minimum angular size, and as you go further, it will start looking larger and larger again. And that's what that means here. The angular size as a function of redshift has a maximum. And in fact, in the Einstein de Sitter universe, that happens at a redshift of 1.25, which is very close indeed by current observations. In a low-density universe, it happens at a redshift of about 4. And that's the refocusing of the past light cone. Now, these are world lines of matter here going up. The world lines are expanding away from us. Our world line is the central one. But we want to look at causality. We want to see at which other galaxies we can see. And it's very difficult to see in this diagram because everything crunches up at the origin. So what we need to do is do the Penrose trick, go to a conformal diagram like that, in which we change the coordinates. These are now co-moving coordinates. The galaxies are now staying at the same value. So that's a galaxy world line there. And we've done a conformal rescaling of the time to make the null cone plus or minus 45 degrees. And that's a Penrose diagram then, again taken from Ned Wright. And what this does is it enables you to see the following. Here we are here. Here's our past light cone. Now, of course, this is exactly the same. This picture and this are the identical space-time in two different coordinate systems. But what happens here, looking down here, the light we are receiving now traveled up this light cone here, and it hit the Big Bang at this instant here. This is the start of the universe at the bottom there, and that's the light cone on the other side. Now, what that means is, over here, there is the present day horizon, and that is the particle horizon. This particle there is the furthest particle with which we can have had any causal connection. So if there's a particle outside there or outside here, we can have had no causal connection with it, whatever. There used to be a lot of confusion about this in the 1930s, 40s, 50s, and Wolfgang Rindler was the person who really clarified this. And so, but in this diagram, it's extremely clear. We can have had this galaxy here. It was born. It's the matter out of which it was made was born there. This is its world line. At this instant, it emitted light, which we receive there. A galaxy there will do the same. We receive light from there. A galaxy there. That galaxy, this matter, is the furthest matter with which we can have had any causal contact, whatever. And so there is a large part of the universe which we cannot ever have any interaction with, whatever, unless the universe is spatially closed. Supposing that world line there was the same as that world line there. Supposing it closed up on a scale less than the size of the horizon. In that case, we would have what we call a small universe. And we would be able to see in that direction in the sky, the same galaxy in that direction. We would see the same galaxies in many different directions in the sky. And I've thought about this a lot. Jean-Philippe Uzan has thought about it, and others. It is possible, because the Einstein equations do not determine the topology of space-time. It is possible we do live in a small universe and that we are seeing the same galaxies in different directions of the sky many times over. I'll return to this in a while. Unfortunately, it looks as if this may not be the case. But unless that is true, there's vast domains out there with which we have no information whatever. But more important for observational cosmology, the entire hot Big Bang section of the universe is scrunched up between that dotted line and the singularity. This is the last scattering surface when the microwave background radiation was set free, and between there and there the universe is opaque. So in fact, from electromagnetic radiation we can see nothing down there, and this line here is the visual horizon. It's where our past light cone intersects the last scattering surface. That's actually a two-sphere. That point there represents a two-sphere, and it's a two-sphere which you see in all those maps of the cosmic microwave background radiation. That is the two-sphere where our past light cone intersects the surface of last scattering. And that is the furthest that we can see by any electromagnetic radiation of any wavelength, whatever. There's a similar horizon for neutrinos, and there's a similar one for gravitational radiation. So there are visual horizons for electromagnetic radiation, for neutrinos, and for gravitational radiation. And what this means is you can make any theory you like about what's out here. You can assume, like when I was young, when Herman Bondi wrote his book, You can assume the universe is identical Robertson Walker stretching out to infinity. You can assume it's a chaotic inflationary cosmology. You can assume anything you like. You can assume that eventually we live in a bubble of matter and eventually the universe becomes asymptotically flat. You can assume we live in a bubble of matter and eventually the density rises and we're surrounded by a singularity. You can assume any of those things. Nobody can prove you're right and nobody can prove you are wrong. So there's a fundamental limitations. And of course it's caused by the fact that the speed of light is finite. And that we live in a space-time. Incidentally, the present scale of the visual horizon is not 14 billion light years as you might think, because the Hubble time is 14 billion years. It is 42, and the factor 3 comes because of it's the integral dt over a of t, which determines the size at the present day is determined by the integral dt over a of t. Okay, now, structure formations in homogeneity. Gravitational action forms structures, and we need to have the perturbation equations. And they are geometric perturbations, and they can be split into scalar, vector, and tensor. And one of the most important papers in cosmology is Lifshitz in 1946, where he pointed this out. And again, Newtonian theory trailed way behind. Bonhoff did the first similar analysis in 1957. They suffer from the gauge issue, which I will talk about in detail in just a minute, and it doesn't occur in the Newtonian cosmology. We get matter perturbations, which underlie structure formation, and nowadays this is heavily tied into the theory of inflation, and it is tied in, as I recently mentioned, into dark matter, that the structures we see could only come into being if we assumed dark matter exists and a cosmological constant exists. So you've got your matter perturbations, you've got your radiation perturbations. These are for time-like particles. These are for particles that travel on null rays, and for that you need relativistic kinetic theory. And this is used to calculate the cosmic background radiation power spectrum. And then gravitational radiation, which enables us to see the furthest out of all of this. And of course, one of the predictions of general relativity was gravitational radiation. And when these telescopes come online, they will give us cosmological information. And then these interact, the gravitational radiation interacts with the microwave radiation to give you polarization, as is nowadays famous. Now, the gauge problem. And we heard discussion of the gauge problem in other contexts a day or so ago. One can choose a constant time surface so as to make a density in homogeneity. No, you define the density in homogeneity in terms of a time. It's the density at time t at point x plus delta x minus the density at times the same time t at x. So that's the obvious definition of a density perturbation at time t. You can make it vanish simply by choosing t as constant surfaces to be the same as the surfaces of constant density, because then that density is the same as that one. Rho at t x plus delta x is the same as rho t, because you've chosen your surfaces of constant time to do that. Delta rho is known, and so defining delta rho in the obvious way is no physical meaning. That's a bit of a problem for us, isn't it? The value is arbitrary because of the coordinate freedom. T goes to t primed as a function of t allowed by general relativity. And this is apparent density violations, in fact, gauge modes. And a lot of the early literature on cosmological perturbations, people were deriving modes which were just gauge modes, and you could just get rid of them by choice, a coordinate choice. The problem doesn't occur in Newtonian theory because you're not allowed to vary your time surfaces in Newtonian theory. Now, the way that I prefer to do this is the 3+1, Bardeen wrote a major paper about this, which proposed a way of doing this which is almost universally used. It's very, very important. It should have been referred to up there. And he derived a way of doing this, what I would call gauge covariant rather than gauge invariant. But his method can be used to eliminate the gauge modes and focus on the physical modes. I personally prefer what I think of as a more geometrical way, using the gauge invariance and covariant formalism, centering on the co-moving fractional spatial density gradient. So what you do is you take the spatial gradient of the density seen by an observer, divide it by rho. That makes that dimensionless. It makes it independent of the dimension of rho, and that is the co-moving fractional density gradient. Now that is a good quantity. For an observer with 4 velocity rho, this is what you measure as the density gradient, because it's a spatial gradient which you and your rest frame measure by any local measurements you do. And the reason this is good is because of Sachs' theorem, which Stewart and Walker pointed out many years ago in a paper that they wrote. Any quantity which vanishes in the background space-time is gauge invariant. And in fact, that's obvious if you go back to the previous line. If you have a quantity there which is invariant, then you can't get rid of it by this trick because it remains the same. And so what you do is you go to the 1+3 covariant formalism, and you look for variables in a geometrically preferred frame to go to the Ricci eigenvector frame in order to have a specific, well-determined frame. And then the fluid acceleration, shear, and vorticity are all gauge invariant variables because they vanish in a Robertson-Walker model. The Weyl tensor electric and magnetic parts are gauge invariant because they vanish in the Robertson-Walker model. And the spatial density homogeneity, pressure inhomogeneity, and expansion of the inhomogeneity of the gradient of the expansion are all gauge invariant variables because they all vanish. And so this is a good set of variables to use in examining inhomogeneity in a perturbed Robertson-Walker model. Now, you can do this in a very, very pretty kind of way. Take the spatial gradient of the general form of Ray Chowdhury's equation, which I had written up. Take the spatial gradient of the density conservation equation and put them together. When W is P over rho is constant and lambda is naught, the linearized growth equation, which you get is a very pretty equation like this one, where n is the wave number. Second derivative of the perturbation, there's a term which says that the perturbation dies away with the expansion. There's a term which depends on the energy density in the equation of state, and there's a term which depends on the wavelength. This directly gives the general relativistic version of Jean's length. The Jean's length is what happens in a static case. So get Jean's length, put theta to 0, and you get an equation which tells you the competition between gravitational attraction, which is this one, and the pressure perturbation, which is this one, and it tells you when the gravitational attraction will win over the pressure or vice versa. So you get a Jean's length general relativity version out of this. In general, this tells you how density inhomogeneities will grow, and when W is naught, that is in the pressure-free case, it reduces to this equation here, which gives the standard results which Lifshitz derived in 1946. And this is really important because we've now got the background models and we've got the way that structures grow in the background models. But we want to do the microwave background, so we need general relativistic kinetic theory. Now this was developed by Singh, Ellis, and others, Sachs. You need a distribution function. Let the photon have an energy E and be moving in a spatial direction, little e, so that's a unit vector orthogonal to O, and you expand the distribution function in powers of the direction E, in a tensor powers of the direction E. So this has got no direction, that's got one direction term, that's got two, and that's got three. And these functions here are projected symmetric trace-free tensors. And that's crucial. Kip Thorne pointed this out, Felix Pirani pointed that out. This is a way of doing harmonic analysis in a beautiful tensor kind of way. And so you split up your distribution function into a scalar part, a vector part, the first tensor part, the higher order tensor parts. And in that case, just thinking, we're thinking of radiation, so the pressure is a third of the density. The stress tensor is expressed entirely in terms of the first three of these, the scalar, the vector, and the tensor part. So the density is an integral of the scalar part, the heat flux vector is an integral of the vector part, and the anisotropic pressure is an integral of the tensor part. And the total mass energy tensor comes from putting those into there, and that enters the Einstein field equations. None of the higher order terms enter the high Einstein field equations. And so this is a very pretty way of relating the anisotropies in the radiation to the density, the heat flux, and the anisotropic pressure they called. You put them in there, put them in the Einstein equation, and that tells you how the radiation is affecting the space-time. But you need the Boltzmann equation, and so you go to the exact nonlinear Boltzmann equation. And this is the exact nonlinear Boltzmann equation. It's a really complicated equation. In general, it relates 5 consecutive moments. The nth one to the n plus 2, n plus 1, n minus 1, and n minus 2 are related by this equation. There's a Boltzmann source term. There's the time derivative of this general one. It decays away according to the expansion. It depends on the spatial derivative. It depends on its divergence. And the prime is the derivative with respect to energy. The prime's derivative with respect to energy. It depends on the vorticity. It depends on the shear. It depends again on the shear. And here again on the shear. And so this is not surprising. When the fluid is shearing, it affects the isotropy of the radiation, which move with that 4-velocity measure. And this is the generic Boltzmann equation, which you can then linearize and work out what happens in particular cases. And the particular paper which does this very beautifully is Chanelor, Lewis, and Lazenby, this particular one here. And this is now standard cosmology, and it's very complicated stuff putting this all together, but and I'll come to that in half a minute. But the question which arises, we're looking at inhomogeneity. So the further question which arises, can we test the homogeneity of the universe? Is that perturbation theory okay? Or do we need to think that the universe isn't just a perturbed Robertson-Walker model? Maybe the Copernican principle is not true. Maybe the universe is not well represented by a Robertson-Walker model. Can we test the homogeneity of the universe? And the point here is the following. We see down our past light cone. We cannot tell if the variations we see, which we interpreted as acceleration, are due to the thing changing in time, which is the standard interpretation. Could they be due to things changing in space instead? Could we be near the center of a great big void in the universe? And the apparent acceleration is telling us not that the universe changes with time, but that it changes in space. Number counts, store statistics, in principle can tell you this, but they actually can't do it in practice because number counts depend on knowing if the source is a standard candle and they are not. And in fact, it's been known since the 1960s. If you assume that radio sources have the same brightness, you don't fit any Robertson-Walker model, whatever. You have to have source evolution. And so you can't interpret the cosmology observations without knowing the source evolution. You don't know the source evolution and you get stuck. You can't get a conclusive result without standard candles with known evolution, which I've already mentioned. But you can if you have standard candles like that. And what you do is you calculate omega k, which is h is a function of z. The derivative with respect to z of z squared minus 1 over h naught dz squared. And that is a constant with redshift. If that stays constant, if you can measure that at all redshifts down the light cone and shows it takes the same value, you have proved that the Robertson-Walker geometry is correct when not at the center of a great big inhomogeneity. You can look at time drift of cosmological redshift, which Jean-Philippe Rouzan and I wrote about. But it turns out that the best way to test whether we're at the center of a great big inhomogeneity or not is to use the kinetic Sunyaev-Zeldovich effect and study the cosmic microwave background spectrum. And I won't go into the details, but that probably rules out these inhomogeneous models. Okay. Gravitational lensing, the bending of light by matter, gives you predicted by Einstein in 1917, gives you strong lensing, it gives you arcs and rings, it gives you weak lensing, and it gives you a cosmological tool detecting dark matter. And lenses are now part of telescopes. They enable us to see further, and they are a key cosmological tool. And so what Einstein started out, at first it was thought it would never be detectable, either for stars or for galaxies. Well, no, for stars it would be, but not for galaxies. It turns out it's a key cosmological tool. Lensing is used to determine the density of dark matter, and this is from the Hubble Space Telescope, from the lensing which they have observed. And it affects the observation of the microwave background because the radiation coming to us from the microwave background is bent by the intervening matter. And so when you analyze the Planck data nowadays, you have to look at the effect of gravitational lensing over the whole sky. So we have now the standard picture of the way that things work. And you start off at some unknown quantum epoch. You have an inflationary era driven by some unknown quantity, the inflaton. You have then, it changes to matter and radiation. You then have decoupling on the surface of last scattering, and that's the surface we see by the Planck satellites. You have the dark era before the first stars form. You then get stars and galaxies forming, second generation stars and galaxies. You get life forming up here, and we're up at the present day here. And this is now the standard model of the way that the universe works. And the evidence this is correct, this is this amazing diagram, the cosmic microwave background power spectrum. This is multipole moment, which means these are small angles here and large angles here. This is the intensity. And the theory predicts these peaks like that. And the theory and the observations are very, very good fits. An incredibly impressive achievement that this theory of structural formation in the universe gives you that fit. Now, we have to use the observations to fix one of the parameters in the theory is a free parameter which you fix by the observations. And otherwise, this is now a verification that this theory of fluctuations does fit what is actually out there in the real universe. That's the microwave background, and there's a similar picture for the matter. And for the matter, you measure using, we've got these huge surveys now, millions of galaxies with redshifts, and you look at the power spectrum of these, and you get a lump there, the baryon acoustic oscillation peak, which is that peak there in the microwave background spectrum corresponds to that peak there in the matter spectrum. And so the perturbations of the matter and the radiation fit together in the most beautiful kind of way. Is it a coherent picture? Well, the puzzles, we don't know what the dark matter is, we don't know what the dark energy is, and we don't know what the inflaton is. So we've got a picture in which it all fits together, but we haven't identified any of the three major dynamical components. And this comes back to something which always worried Einstein. The result of using the Einstein field equations depend on the right-hand side, and in this case, we don't know what they are. We can look at alternatives and isotropic models, which I've spent a lot of time on, the inhomogeneity models, the Lemaitre-Tolman-Bondi model, and I've already talked about that. In principle, you can use that to get models with no dark energy. In practice, it doesn't work because of the Sunyaev-Zeldovich effect. I've talked about small universes, and just one comment on that. I would love the universe to be a small universe. I would love it to be a universe in which we've already seen everything which existed. There are various ways of testing for it, but the best test is to look, if we lived in a small universe, there would be a circle in the microwave background sky here, where the specific pattern of microfluctuations is the same as another circle in the microwave background sky over there, and another one over there. And there's a whole lot of work being done, and again, Jean-Philippe Rouzan has looked at this, relating possible circles in the sky, in the microwave background sky, to the possible topologies of the universe. They've been looked at in simple cases, and it looks probably that this isn't the case. The most sensitive tests of the nature of the universe come from structure formation, cosmic microwave background anisotropy, which are the effects of the universe on local physics. And I just want to point this out because this is really interesting. This is the standard diagram. The matter density this way and the curvature, the dark energy density this way. The supernova data limit you here. The baryon acoustic oscillations, which I showed you the details there, that's the fluctuations in the matter and radiation in the hot Big Bang era, limit you here, and the cosmic microwave background radiation limits you there. Now, the point about this is the following. The supernova observations are direct observations of the geometry. They are, in fact, using the magnitude redshift relations with the supernova as standard candles. And so they don't use perturbations. They are direct measurements of the geometry, assuming we've got standard candles. By contrast, the fluctuation here, it depends on the way the fluctuations work, and it depends on omega and omega because the cosmological context changes how these fluctuations work, and then these fluctuations then propagate to us, and the cosmic microwave background gives it. And the thing I want to point out is the following. If you take just the baryon acoustic oscillations in the cosmic background, you end up in this tiny part here. You get much better limitations on cosmology from the perturbations of the matter and the radiation than you do from the direct test by the supernova. This gives you much weaker. If you just had the supernova, we wouldn't have tied down the parameters at all. We require this one and this one to tie down the parameters. So the theory of fluctuations is what enables us to test the universe model very, very precisely. Okay, this is now my final slide, except for the summary. One of the themes in cosmology is the unification of physics and cosmology. In the first one, there's a series of unifications. And cosmology, this is its progress in physical science. The first one was gravity. Apples, the moon, and the universe, gravity is geometry. And this was what Einstein gave us, that the same force which makes apples fall to the surface of the earth, which makes the moon go around the earth, is the one which controls the universe. That's an incredible unification, the first unification of physics and cosmology. The second one was atomic physics and quantum theory, and this was Gamow, not Tolman. Now, Tolman should have seen this in 1934 when he wrote a book called Relativity, Thermodynamics and Cosmology, but he missed it. Matter-radiation equilibrium and recombination leads to the prediction of black body radiation, and we've seen it, and so this gives you a unification between atomic physics and cosmology. The third unification was nuclear physics. Nuclear reactors can be used to tell you what nuclear synthesis should work in the early universe. Alpha and Gamow and Peebles particularly worked on this. And it was when nuclear synthesis came in and became an established part of cosmology that the physicists recognized cosmology as a branch of physics, and this was marked by the fact that the particle data group then included cosmology in their annual survey of particle data. In principle, so we've had the unification of gravity, of atomic physics, of nuclear physics. Now, inflation was supposed to unite particle physics with cosmology, and this was Guth, Steinhardt, and others, but it hasn't worked unless the inflaton is the Higgs. Because if you look at the literature on inflation, none of it is tied into real physics. It's all phenomenology. It's all just assumed behavior of the inflaton. The only case in which you can tie a potential inflaton into experiments that we do is the Higgs, which of course has been tested at the LHC. And then, of course, the final one, quantum gravity and creation, quantum cosmology. This would be the final unification of some theory of quantum gravity and creation of the universe. And we are not on solid ground here. We can hypothesize many, many possibilities, but there's no real tests. So, general relativity has made present-day cosmology possible. The standard model vindicated by observations, and I've shown you these wonderful observations due to these current telescopes. This is one of the great triumphs of GR, together with black holes, gravitational radiation, and GPS systems, and Einstein started it all off. His greatest blunder was missing the expansion of the universe and denying it when Friedman pointed it out. It's actually quite sad, that one. It's a bit like Eddington and Chandrasekhar. The greatest development of the theory is not so much the background model as the perturbations about it, and handling the gauge issue is crucial. And so I hope I've given you a feeling for that cosmology, it started off being the dynamics of the background model, but it transitioned in the past 20, 30 decades into being a very, very detailed, astrophysically tied in study of perturbations about the Robertson-Walker model, handling the gauge issue, and the Bardeen method is the most widely used way of handling the gauge issue, and getting these predictions for structural formation, microwave background anisotropies, testing them with observations, and getting a unified whole.
Yeah, we're bit late, but we could take one or two quick questions. Okay.
Okay. At the beginning, you talk about a lambda decaying when you do a picture of a set. Okay, okay. And I didn't understood well what we meant. What you meant by decaying lambda? Is it an equation of state, or is it a lambda that is decaying from of t, something like that?
If we don't know if the acceleration is caused by a dynamic field or by a cosmological constant, and people loosely talk about a decaying cosmological constant. Of course, a cosmological constant can't decay, but we use it as a loose term to mean a dynamic matter field. If the cosmological constant is a real cosmological constant, the future of the universe is fixed. It will expand forever. Nothing interesting will take place in the future, and that'll be the end of everything. But it may still, but there's a huge effort trying to find out if it's actually constant or not. A lot of observations are being done to try to find that out. And if we find out it is either growing larger towards the future or smaller, this completely changes what we can say about the future.
Okay, so I think people are looking forward to the topic. So let's thank you again.